Welcome to the LMWC Learning Mathematics with Ms. Choekyi channel. Please do hit the like button and subscribe the channel.
Hello everyone. So we are going to start the chapter number 1, which is real number, and in real number the first topic is fundamental theorem of arithmetic. So to understand this theorem, we have to understand the definition of composite and prime number. So prime numbers are the number which has exactly two factors, and the two factors are the number itself and the number 1. So let's just quickly take out the first few prime numbers, and those are number 2, 3, 5, 7, and likewise. Whereas composite number is the opposite of prime number, which is it has more than two factors. So more than two factors, let's quickly take out the first few composite numbers, and those are the number 4, number 6, number 8, number 9, number 10, and likewise. So understanding the definition of prime and composite, let's quickly try to read this theorem. So this theorem says every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factor occurs. So here what you need to understand is that you are given a composite number, and that composite number you have to express it in the form of product of primes. So as you can see, this number 2, number 2, number 2, between all these two you can see the product form, the multiplications. So what it says is that composite number can be also written as product of prime numbers. So that is what the fundamental theorem of arithmetic says. So if we take another example, I have written it here, number 14. So number 14 is a composite number because it has more than three factors. Number 1, number 14, as well as number 2 and number 7 as well. So since number 14 has more than two factors, so therefore this is a composite number, and this composite number, it can be expressed as a product of primes. So we have taken number 2 and number 7, which are primes, and if we multiply these two, you're getting the number 14, which is a composite number. So that's what the fundamental theorem of arithmetic says. So moving forward to the next topic. So next topic we are given one formula, and the formula is HCF times LCM is equals to A times B. So you are given two numbers, okay, any two numbers, and if you take the product of those two, this will be equals to the product of the HCF of the same A and B and LCM of both the A and B. If you take the HCF and LCM of the two numbers A and B, that will be equals to the product of those two numbers itself. So this is what the formula says. Now using that formula, we will try to do one example so that it will be much clear for you. So the example is find HCF and LCM of these two numbers 6 and 62 using the prime factorization method. So now prime factorization method is, we do it this way. We take a horizontal line and a vertical line, and we take both the numbers, which is 6 and 62. So you take the number like this, 6, 62. You take the comma to take the partition of those both the numbers. Now what you're going to do is, at this side, over this side, you're going to write down the prime number. Since it's a prime factorization, so you're going to think of only prime numbers. So let's quickly go back to the prime numbers. So prime numbers 2, 3, 5, 7, 11, and likewise, right? So you're going to think of try to always think for the smallest prime numbers. Always starts with the smallest prime number and see whether it is factor of both 6 and 62. Now, since 6 and the 62 both are even number, I will start with the even number itself, the prime even number, which is 2. So 2 times 3 is 6, 2 times 31 is 62. Now again I need one more prime number. So here I need one more prime number which is a factor of both 3 and 31. But unfortunately we do not have any prime number which will give the product of both 3 and 31. Right? So here we will stop the prime factorization method, and this number 2 is your HCF. Okay, so the HCF is, to find the HCF you have to do it in this manner. You have to take the common factor of both the numbers. Until and unless you are not able to find the factor for both the numbers, you are going to stop there like this. So now the HCF of 6 and 62 is number 2. And I have written it over here. The solution is already written here. Now let's move to the LCM. So to find the LCM, I'm going to follow the same method, except the only difference is that here we have stopped until 2. But in here, we will not stop at 2. So let's see how different it is. So again, we will start with 2, 3, 31. Now, here 3 and 31. For the HCF is concerned, we have stopped because we are not able to find a prime number which is a factor of both 33 and 31. But for the LCM, you need not have to worry about that. You have to focus on, if you are not able to get both the factors, you can focus on any one of them. So now I'm going to focus on the first digit, which is 3. I'm going to convert this 3 to 1. So to make that, I can think of the next factor, which is 3. So 3 times 1 is 3. Now what about 31? So 3 times what is 31? We do not have. So at such situation, you are just going to take down this number as it is. All right. Now the next number will be, you have to think it in this way, that now since the first number has been converted into 1, now I need to focus on the second digit, which is 31. Now I have to make this 31 into 1. So to do that, I have to think of a prime number which is a factor of 31. So if you think, you have only number 31 itself, and number 31 itself is a prime number. So 31 times, so since this has been converted into 1, you will just take the 1 as it is. So 31 times 1 is 31. So the moment you have converted the quotient 6 and 62 into 1, 1, you will stop the LCM, and the number which is over this side are your LCMs. So you're going to take the product of these 3. So 2 times 3 is 6. 6 times 31 is 186. All right, so the HCF is 2 and the LCM is 186. Now we have found the HCF and the LCM of both the numbers. So here, keep in mind that both the number means the 6 is your A according to the formula, 62 is your B according to the formula. Now your job is to verify whether the LCM and the HCF which you have just found is correct or not. So in order to do that, I am going to use this particular formula. So now what I've done is I've just taken the exact formula over here, HCF, except that A and B I have replaced as per the question, which is 6 and 62. So HCF times LCM equals to A and B, which is 6 and 62. Now what I will do is I'll just copy down HCF as number 2 and LCM as 186, and that is equals to take the product of 6 and 62, which is 372, and 2 and 186, just take the product and you will get as 372. So this shows that the HCF and LCM which you have just found using the prime factorization method is correct. So this formula is just to make sure that your HCF and LCM is correct, and this is just for the verification of that. Okay, so moving forward to the next topic. So next topic we have a theorem. So as per CBSE syllabus, you just need to understand the statement of this theorem. So with the help of this theorem, we are going to solve for questions of this type. Okay, so now let's move to the theorem. So this theorem says that you have a prime number which is b, and that b, if it divides a square, then the same b has to divide this a, where a is a positive integer. Okay, so let's think of a positive integer. So we have, so positive integers, we have, what do we have? 1, 2, 3, and everything, right? All the counting numbers. Now I'm going to consider a as number 2. Okay, so number 2 is in this, right? We can find number 2 in this. So I'm going to take any one of it, and that is number 2. Now if I square it, what will happen? It will be 2 square, which is 4. Now I'm going to think a prime number. All right, so prime number. So let's quickly list out few prime numbers, and those are 2, 3, 5, 7, likewise. So in this prime number, I am going to take the p as the first prime, that is 2. So according to the theorem says that if p is a prime number, which is 2 is a prime number, right? If p is a prime number and a is any positive integer, so I have taken the positive 2 plus 2. Now, if that is the case, and if p divides a square, so divides means here it says a square is divided by p, which means a square according to here is 4 by, take the p as, replace it with 2. Now, does this 2 divides 4? Yes, 2 times 1, 2 times 2. So this fraction has been converted into number 2. Now, in such case, it says, it means that p divides a square. This is how you read it. Now, if that is the case, then this particular p has to divide a also without the square. Now, let's see if it's true or not. So let's just replace the a with 2 and p with 2. So 2 times 1, 2 times 1. Yes, it does divide. So this is what the theorem says. So let's quickly read the theorem to make it more clear. So let p be a prime number. If p divides a square, then p divides a also, where a is a positive integer. Now, having understood this statement, we are going to solve this kind of example. And this kind of a question is very, very important, and it's going to come in the board for sure. All right, now let's prove this example. So this example says, prove that root of 2 is irrational numbers. So everyone knows that root 2 is indeed an irrational number, but how will you prove it? So to prove this, we are going to use this theorem, okay? So to prove, we are going to use the method which is called as contradictory method. So in contradictory method, what we will do is we will try to assume something, but while proving that assumptions, we will get to know that our assumption was incorrect due to contradictions arising in between the proof, and hence we will conclude that the assumptions which we have done in the beginning was incorrect. All right, so this is the contradictory way of solving such kind of questions. So we are going to use that method here. So here what we are going to assume is the given question is root 2. We are going to assume this as the opposite of irrational, which is rational numbers. So let us assume root 2 is a rational number. So the moment you have assumed root 2 as a rational number, you have to use the definition of rational number, which is a by b, right? In the form of p by q, if you remember. So root 2 is equals to a by b because we have assumed root 2 as rational numbers. And where a and b both are integers as well as they are co-primes. So always keep in mind that co-prime, if I give an example that will be much clearer for you, you're going to take a and b, both are integers, so 2 and 3 are integers, and their common factor is 1. So there are no other common factors of 2 and 3 other than 1. So such kind of number are called co-prime. All right. Likewise, if I have to give another number, 11, 12. So it has a common factor as 1. So 1 times 11 is 11. 1 times 12 is 12. So 1 is the only common factor for both the 11 and the 12s. Likewise for all the numbers. Now, after assuming this, so what we will do is, the first assumptions which we have done, we will simplify it like this. We will take the b and root 2 as a cross multiplication. So this will be a equals to b root 2. After that, since we have a square root over here, we have to eliminate this square. So I'm going to take the square on both sides. So taking the square on both sides, so b will have a b square and root 2 whole square will be 2, and the root 2 will get cancelled. So only 2 will be left. Now, at this stage, what you will do is you have to take this 2 to the denominator, because you have to write it in this way. The p will be in the denominator. So likewise here 2 will be in the denominator. So once you have taken this 2 over this side, it will become b squared is equals to a squared by 2. Now a squared by 2, if you go back to the theorem, it will be a squared by p. Likewise a squared by 2. So now 2 is a prime number, right? So here the a squared divides by p, then according to the theorem, p should also divide a as well, right? So that will be your first equation. So if I have to write it in the word, it will be, which implies 2 divides a square. Also 2 divides a from the above theorems. So the theorem we just mentioned over here, right? Now that will be your first equations. Now I need to derive one more equations. So the second equations, to derive that, I am going to consider a letter c, and c is any integer. So here a is equals to 2c, where c is any integer. So please keep it in mind that 2, why we have taken 2? Because we have to prove root 2, right? So whatever is number inside the root, that you will going to consider it. So a equals to 2c. So squaring both sides, a squared is equal to 2c squared. So a squared, we have from the equation number 1, we have replaced this a squared. Now going back to the first here, a squared is 2b squared. So I'm just going to replace this a squared as 2b squared. The rest is same. So 2 times 2 squared is 4, c squared is c squared. Now I'm going to cut this one. 2 times 1, 2 times 2 is 4. So b squared is equals to 2c. Now I'm going to take this 2 to the denominator of b squared. So the moment I do it, I'm just left with c squared is equals to b squared by a, right? So again, what happened is, which implies 2 divides b squared, then 2 must also divide b as well. So what we have understood from equation number 1 and 2, that a is divided by 2 and also b is divided by 2. So which indicates that the number 2 is common factor of a and b. But in the beginning, what we have considered is a and b has only common factor as 1, which is a co-prime, right? But what we have just understood from the equation number 1 and 2, that a and b has another factor, which is number 2. And this contradicts the our assumptions, because we have assumed a and b has only one common factor, that is 1. But here there is another common factor apart from the 1, which is 2. So hence from equation 1 and 2, a and b have at least 2, the number 2 as a common factor, which is a comma b is equal to 2. And this contradicts the fact that a and b are co-prime, and this contradictions occur due to our incorrect assumptions. So if you remember in the beginning itself that we will be using the contradictory way to prove such kind of equations. So this is how you do it. So the moment you get the contradictions, so this contradiction arises. Why? Because of the incorrect assumptions. So our assumption itself is wrong. So what was our assumptions? Our assumption was root 2 as rational numbers, right? So now if root 2 as a rational number was wrong, then what does it mean? So it has to be the opposite of rationals, and that has to be irrationals. And that is how you prove such kind of equations. I hope you have understood everything, and please do like the video and subscribe the channel for more videos in the future. Thank you.